Hello everyone, my name is Johanna Vielhaben, and in this video I will talk about our new method for concept-based explainable AI, which we call multidimensional concept discovery, in short MCD. Due to their inherent complexity, most deep learning models are black boxes. However, for safe and trustworthy AI, we need to know the model's internal reasoning, in particular for high-stake applications. eXplainable AI methods, XAI methods, allow us to peek inside the black box models. Often, local XAI methods are used to understand the model decision. These methods measure the relevance of single input features for a particular sample. Common choices are layer with relevance propagation, integrated gradients, or Shapley values. A useful property all of these methods fulfill is the so-called completeness axiom. This means that the attributions sum to the final prediction, which ensures a meaningful interpretation of the attribution heatmaps. Now, local XAI methods are very valuable to understand the model decision for a single sample. However, for a more global understanding of the model, the user must aggregate a lot of attribution heatmaps into a common concept the model might be using. This is problematic because it is not clear how the concept the user imagines align with the actual model behavior. This calls for novel XAI methods that connect the global model behavior with decisions for single instances. Here, concept-based explanations come into play. These allow us to understand shared model structures for an individual sample. In recent years, multiple concept-based explanation methods have been proposed. The first question each of these methods has to answer is, what is a concept? Now, concepts are inherently linked to activations of a hidden model layer. Thus, the question now is how to meaningfully decompose the feature space that these activations form into concepts. Here, we give an overview over what linear structures the concepts could possibly form in feature space. To illustrate these definitions, we use a simple example. We consider the activations of a last convolutional layer just before average pooling in a linear classification head, like in ResNet. These activations form feature vectors phi with as many entries as there are convolutional channels F. All possible activations phi now span the feature space that we want to decompose into linear structures to find concepts. The first definition, D1, identifies each convolutional channel with a concept, and thus decomposes the feature space into single channels. Definition D2 is slightly more general and allows concepts to form orthogonal linear combinations of convolutional channels. Definition D3 drops the orthogonality constraint and allows arbitrary directions in feature space. Now, for our method, MCD, we propose a new definition, which is multidimensional subspaces of arbitrary rotation. This definition, D4, allows a concept to lie on a hyperplane spanned by multiple directions of the convolutional channels. This is the most general linear structure concepts can possibly form in feature space. With definition D4, one can capture any meaningful linear structure in feature space. Thus, it enables the most faithful concepts among the discussed definitions D1 to D4. Another benefit of multidimensional subspaces as concepts is that they ensure concise explanations. This is good because it is difficult for a user to overlook a large number of concepts in an explanation. Thus, we want to cover the feature space with only a small number of concepts for the explanation. And with multidimensional concepts, we can avoid a fragmentation into many low or one-dimensional concepts. Lastly, with MCD and definition D4, we re-establish the often desired completeness property for concept explanations. This means that the relevance scores we assign to each concept sum up to the final prediction. I will come back to these concept relevance scores later. Here we list the three elements of concept-based explanations: concept discovery, concept presentation, and concept relevance. We will now introduce the MCD solutions to these elements. We argue that every concept XAI method has to formulate an approach for these elements. The first element is concept discovery. This happens in a hidden layer of the model. So before concept discovery, we split the model into the part H that maps the input to the concept layer activations phi and the part G that maps these to the predictions. Then the MCD concept discovery has 3 steps. First, we randomly choose a set of feature vectors from a selection of samples. When we want to discover class-specific concepts, we choose only samples from that class. Second, we cluster the feature vectors. This step is modular, and in principle, we can choose any clustering algorithm. To discover multidimensional subspaces as concepts, sparse subspace clustering is a particularly well-suited option. Third and last, we construct a basis that characterizes the concept subspaces using the cluster members from the previous step. For this, we first estimate the intrinsic dimensionality of the subspace and then use PCA to construct the basis vectors. The second element is concept presentation. The raw feature space representation of the concepts is not comprehensible. Thus, we need to present the concepts in input space and demonstrate their essence, for example, by concept prototypes. So far, the raw feature space representation of an MCD concept is a basis for a linear subspace. To show how a concept is expressed within a particular sample, we construct concept activation maps. To this end, we decompose the feature vectors phi of the sample into concept contributions. For the decomposition, first we have to make sure that the concepts span the entire feature space. Thus, we define an orthogonal complement to the concept space, which is the union of all concept subspaces. Now, we can uniquely decompose each feature vector phi into its concept parts. We interpret the L2 norm of these concept parts phi L as the activation of the concept L within the sample. This activation, in other words, is the extent to which concept L is expressed in the sample. Finally, to represent concept activation maps in feature space, we simply resize the concept activation map from feature layer size to input layer size. Finally, as prototypes, we select the samples with maximum concept activation. The third element of concept XAI methods are concept relevance scores that quantify the contribution of each concept towards the prediction of a specific instance. Additionally, we can find concept relevance scores on a global model level. Similar as for the concept activations, we can decompose the final prediction into concept contributions for the MCD concept relevance scores. To this end, we specialize to a last hidden layer, which is only followed by linear operations. For example, mean pooling and a linear classification head like in the previous example. Then, a class logic up to the bias term is the dot product between the corresponding weight vector W of the linear classifier and the feature vectors phi after pooling. Again, we can decompose the feature vector in the dot product and get a relevance score RL for a concept CL. Importantly, these local concept relevance scores sum to the logic minus the bias. In this way, MCD reintroduces completeness to concept explanations. We can perform this concept decomposition on the feature vectors before pooling to get a concept relevance heat map. This can be again resized to the input width and height to represent it in input space. Additionally, MCD defines global concept relevance scores, for which we refer to our paper. Now we have introduced all the components that make up the final MCD explanation that this slide shows. Here, each column represents a concept. On the upper part, we show the local concept activation and concept relevant maps for the individual sample at hand. The concept relevant heat maps and local concept scores indicate how typical the model perceives the instantiation of the concept in the sample for the class. The concept activation heat maps identify the region of the image where concept is highly expressed. Here we additionally guide the eye with yellow contour lines at a specific threshold. On the lower part, we show concept activation maps for the concept prototypes. We have chosen these by high concept activations. For the class here, which is the policeman class, the concept we have discovered with MCD would be identified from left to right with windows and livery, blue lights, a building and background, which is often there, tires, and then the orthogonal complement mainly covers the background. To evaluate our method quantitatively, we have used concept flipping to measure how faithful the MCD concept explanations are to the model. For this, we flip concepts successively in the order of highest relevance in input space and measure the drop in prediction accuracy. A faithful method should show a steep descent in prediction accuracy. We compare MCD with sparse subspace clustering to MCD with other clustering methods and invertible concept explanations, ICE with PCA by Zhang et al., and then lastly, automated concept explanations by Gorbani et al. We find that MCD SSC shows the steepest descent in prediction accuracy without losing all accuracy by flipping only a single concept. The latter would correspond to flipping the entire object and would thus not be a good concept decomposition. In summary, MCD SSC is the most faithful to the model among all methods in the benchmark. Further, we have evaluated the conciseness of explanations by measuring the mean number of concepts that is required to reach a fixed coverage of the relevant feature space. We further contrast them with other measures such as concept dimensionality and similarity between concepts. We find that MCD SSC is superior in dissecting the feature space into enclosed and meaningful concepts. For details on this comparison, we refer to our paper. Finally, I want to comment on the particular use cases we have in mind for MCD. We believe that MCD is particularly useful for knowledge discovery in the natural sciences. For example, MCD could help to identify subclasses of cancerous cells by discovering concepts for a cancer classification model. Further, because MCD allows to summarize model behavior beyond single examples, it is particularly suited to systematically discover model biases. Lastly, MCD has no interpretability enforcing regularizers that could obfuscate the original structures learned by the model, and thus MCD is the most faithful to the model as possible. This also means that MCD prioritizes faithfulness of concepts over identifiability with known human concepts, which could be seen as a limitation for some use cases. Thank you now for listening to this talk on multidimensional concept discovery, MCD. You can find the link to our TMLR paper at Open Review and the code for MCD in the linked GitHub repository. Thank you.